Okay, we've talked about the different vectors, uh, displacement, velocity, and acceleration. I'll probably from now on be using pretty much displacement and distance, velocity and speed interchangeably. You just have to know that if I'm only giving you a magnitude, that it's not a vector, it's a scalar. So um, now, in this lesson, we're going to be talking about distance versus time graphs and velocity versus time graphs. And so let's just jump into it. And here is a distance versus time graph. I always abbreviate it DVT. You won't necessarily see that abbreviation in IB, but it saves a lot of time with us. Now, we've talked about displacement versus distance, walking from home to school, back home, past home into the negative direction, to get to a friend's house and then back home. Your overall displacement for the day would be 0 and things like that. So we're not really going to cover that again. What I'm going to show is how to graph this, how we're going to represent distance or displacement using a visual method. All right, so let's go back up to our old example and let me get us a good color here. And looking at this, let's say you get up to go to school and you can actually walk very fast. You can walk 1 block in 1 second. Not very realistic, but this makes this demonstration a lot easier. So we've broken up, we'll call it blocks, but it's just 6 equal segments that you walk to get to school. All right, so let's graph how you do this. All right, so at time 0, you're at 0, right? Makes sense. Yeah, let me do something here. All right, so you're at time 0. At 1 second, we're going by seconds here, and I'll talk about the graph setup here in just a little bit. I just want to get a graph set up for you to look at. At 1 second, you've gone 1 meter. At 2 seconds, this is in meters up here, and I'm just every second we've gone a meter so far. So at 2 seconds, 2 meters. At 3 seconds, we'll have gone 3 meters. 4 seconds, 4, 5, 5, and finally we arrive at school 6 seconds later. Don't you wish you could get to school in 6 seconds? Let you sleep in a little bit longer. But oh well. All right, so we have a graph. We can draw a line, and I want to take a side moment here to talk about graphs. You're in an advanced physics class. No longer are you going to just connect the dots on your graphs. You're going to find the best fit line. Not all data, as we know from the summer packet that you did, is going to be exact. You're going to have errors. Things are going to not line up exactly. So you just need to find the best fit line. Now, these should have lined up exactly, but I'm just eyeballing it, so they didn't. But this kind of illustrates what a graph should look like. A general trend in the direction of the dots, and then a straight line through them where you have just as many above the line as below. Not necessarily the case here, but that's okay. They should have been in a straight line anyway, because we have no errors in our little thought experiment here. Okay, so that aside, just keep that in mind. When you do a graph, best fit line and not connect the dots. That's no good. Okay, so we've got our graph here. One thing to note in using any kind of graph that is using time, you know how we have coordinates or quadrants, I should say, on X and Y graphs. We have a positive quadrant here. We have negative here. We have, I should say positive, positive, negative, negative, positive, negative, negative, positive. This is the Y part, and this is the X part. But because time cannot be negative, we will never use this quadrant right here. Either one of these. Time cannot be negative. It only moves forward. So distance can be negative, as we've seen, because if I start from school to go home and I come all the way to home, and then I end up over here at some friend's house, then I've gone in a negative direction. And so distance can be negative, just from whatever our reference point is. Time can never, ever be negative. So we only deal with this quadrant of these two quadrants of the XY plane. Okay, so with that said, let me get this out of the way because it's a little bit distracting. In this case, we've only moved in the positive direction. So there. Now, if we come home, excuse me, if we come home, well, let's say we stay at school, because we've done this before. We stay at school for a certain amount of time, and then we would come home, right? That's what that kind of graph would look like. We'd have a negative slope because we're moving in the negative distance direction, in the direction of the negative for distance. We would never go back in time. We just can't do that. Okay. So we can tell a few things about our motion from this. As a matter of fact, we can tell how fast it took us to get to school, right? It took us 6 seconds. We went 6 meters in 6 seconds. So interesting, let me get back to the right thing here. So the interesting thing about the slope is it tells us our velocity. Remember, very easy equation. Most of you may know this either from Algebra 2 or I don't think you've learned it in pre-calc yet or anything like that. But velocity equals distance over time. And where that comes from is from a graph like this. And remember, I want to do a little bit of vocabulary here very quickly. You've heard miles per hour, right? I should say MPH, miles per hour. Meters per second. I'll just abbreviate that. Whenever you see per there, the per is the divisor in a fraction. If you see per, there's a divisor there, okay? There's a line there. And so that would be miles per hour. So what we have is, in this case, we're talking meters. Meters per second. All right, so that makes sense, meters per second. This means that we have divided the number of meters we've gone, the number of seconds. And IB has a very unique way of writing this, which is actually mathematically a much superior way of writing than this. Meters, seconds to the -1. That is exactly the same thing as meters per second. It's meters per second. We just put a -1 up here. And that helps when we are doing very complex equations with many multiples of different kinds of units in it. And we can have seconds, and let's say we have kilograms per second, and then we multiply by, divide by meters. Well, we can cross off the meters. We have kilogram, second, per square second, you know, that kind of thing. You can just easily add these up and as we go down the line. Okay, so that's all of that. Get rid of that. Okay, so so slope is velocity. And what I mean by that was slope is rise over run, correct? So that means we take the initial distance, I mean the final distance, distance final minus distance initial over the final time minus the initial time. Now we can do this on any part of this slope, right? We can take it from 2 seconds to 3 seconds, from 0 to 6. So let's just do that. Let's go 6 meters minus 0 meters. And it's 6 seconds minus 0 seconds gives us 6 over 6. So our velocity, or our slope, either one, is 1 meter per second. I don't know if you can hear, but my cat's deciding to try to get in on the lesson here. All right, so that is how we determine the velocity from a distance versus time chart. Now that's basically all you're going to be able to tell from that. And if we have multiple sections of time where you stay and you come back, you know, here's a negative slope, so our velocity would be negative. Here's 0 slope, so our velocity would be 0. So we can take different portions, because never during the day do we spend the entire day just going the same velocity. Unless you're like on a spaceship going to the moon and it takes 3 days to get there and you're going 30,000 miles an hour. So for the entire day you're going 30,000 miles. No, we get up, we walk, we ride cars, we run, we do all kinds of things, but we stop at stop signs, you know, we never go at a steady pace. So we always segment what we're doing. Now this brings a point. Well, remind me to get back to instantaneous velocity versus average velocity when we talk about velocity, which let's get right to that now. All right. Oops. There we go. All right. All right. So there's a lot more to talk about here than with distance over time. But let me state this. If you have a distance versus time graph, and you have your distance and your time, and you have just a nice straight slope going on here, that means you have a steady, constant velocity. Like we just calculated that one over there at 1 meter per second, right? The one we just did was a nice slope like that. It was 1 meters per second. On here, that would equate to, at 1 second, we were going 1 meter per second. At 2 seconds, we're going 1 meter per second. 3 seconds, 1 meter per second. And so on and so forth for all 6 seconds. So that would give us a straight line. All right, and it's our velocity is not 0, like this would be 0 distance. We would be not traveling at all. On a distance versus time graph, on a velocity versus time graph, we are at a constant velocity, in this case, of 1 meter per second. Okay, only if we were down here would we be going 0 meters per second, or we would be standing still. When we're on a distance versus time graph and we're sitting still, that would be a 0 velocity. That's what that would be right there. Okay. All right. Okay, so let's though have oops, I moved my thing, so there we go. All right, so let's have a slope on our line. We are not going a constant velocity. Let's say our velocity is increasing. All right, so our velocity is going to increase. Let me get a different color here. And so we have a nice constant velocity. I'm trying to make this look like we're increasing our velocity at 1 meter per second. Okay. Now we have a slope here. That means our velocity is changing. The rate of our velocity is changing, right? It's every second we are going faster. At second 2, we are going 1 meter. At 1 second, we're going 1 meter per second. At 2, we're going 2 meters per second. Give me just 1 minute. There, I just killed my cat. No, just let her out. She wanted to go outside. Okay, so we've got, we're increasing. So I will explain in just a little bit what that does to the distance versus time graph as we increase this. But what happens what do you say when you are, say, going 25 miles per hour and then you change your velocity gradually over time to go 50 miles per hour, 25 miles per hour to 50 miles per hour? What are you doing? You're speeding up. Or when you are going 25 miles per hour and you come up to a stop sign, you have to slow down to stop. So you are changing your velocity, and that is called acceleration. In physics, even when you are slowing down, that's considered acceleration. In this case, called negative acceleration. The next lesson we talk about, we are just going to go into acceleration and tie it into velocity and distance, and we're just going to go crazy on that. But right now, you just need to understand that acceleration is always a vector. You can't say, because it's always got a direction. You're either slowing down or you're speeding up, right? You're either going in the negative direction or the positive direction. That's actually a very big distinction. We'll talk about that next lesson. So it's either positive or negative. It's no doubt about it. There is no scalar for acceleration. I can't even, there's not even a word for the scalar of, like distance is the scalar for displacement. Acceleration is just a vector, and it's always got a direction. So, okay, so we've got velocity, and we've got a constant changing velocity. Well, turns out the slope of the velocity graph is the acceleration. So slope equals acceleration. And so that would be the final velocity minus the initial velocity over the final time minus the initial time. And again, when it's a constant acceleration, that is a constant straight line on the velocity, you can use anywhere on this graph to figure out what that acceleration is. If it's a changing velocity, and if it's a changing velocity, you're going to see something like this, something like this. Anything that is different, well, you're going to have to take an instantaneous acceleration at that point. And we don't necessarily do that here in, we don't necessarily do that here in high school physics. That calls for derivatives, which is calculus. and we're not going to do calculus, especially in IB. So we're not going to worry about instantaneous. Now, there is at least instantaneous acceleration. We are going to differentiate between instantaneous velocity and average velocity. If I have a velocity that is changing, I may want to find out what my average velocity was throughout this whole trip. I will take, okay, I ended up this far along at this time, and I can take that and get my, what was my average velocity for the entire trip. Or I can say for second number 2 to second number 3, I went from position this to position that. What was my velocity for that? We'll consider that an instantaneous velocity. Technically, an instantaneous velocity is right on this point. You draw a tangent to the line and get the slope of that tangent, which is a calculus thing to do. But we will take little pieces of time and find the instantaneous velocities. We'll actually do that when I give you an experiment to do, a little lab activity that we'll do within the next class or two. Okay, so instantaneous velocity is the velocity in that instant or very small amount of time, and the average velocity is over the entire trip. Okay, that's a very important distinction, and you do need to know that. Okay, so back to the acceleration. In this case, our acceleration, we're going to just go with this. We've got darn thing. Oops. How do I move that back? Well, I'm just gonna have to work with this. Don't know how that happened. Okay, well, we'll just go with this. Sorry about this, but it will not move back. And I don't know what else to do. Oh, wait a minute. There we go. Got it. All right, acceleration. And I'm going to save time. I'm going to just call it A. 6 minus 0. I know it looks very much like our distance versus time, but that's just because I'm using the same number line here. 6 minus 0 for the time. And so we get, this is velocity. So this is meters per second, meters per second. So we get 6 meters per second over 6 seconds. So what this is going to equal is 1 meter per second squared. Okay, this is, in other textbooks you see this written like this, meters per second per second. Could write it 1 meter per second per second. What that means is when you see squared, especially for time, is that for every second we are increasing, for every second we are increasing our velocity by 1 meter per second. Okay, if you need to think about that, pause the video and ponder that for a little bit and just make sure you get it. For every second we are increasing the velocity 1 meter per second. That's what 1 meter per second squared means. Okay, so that is how the slope represents the acceleration. The acceleration is the rate of change of velocity. And you may know this, but every time you see rate of change, you're talking about over time, right? So rate of change of velocity is the change of velocity over time. over time. Change in velocity over time. Acceleration equals change in velocity. Delta means velocity over change in time. Okay, so that is exactly what acceleration is. That's exactly what a slope is when you have time on the x-axis, is a rate of change. All right, so that's how the slope of velocity is the acceleration. Now there's one more thing that can be very telling, you can learn a lot from, is that you can take the area underneath the slope of a velocity, and you can find the you can find the distance equals area under v versus t graph. So let's just see if this is true. Well, in this case, we can't say, we don't have anything to compare this to yet. I'll get there. We have a triangle here, and so the area of a triangle is 1/2 the base times the height. In this case, the base is x and the height is y, and so that equals 1/2 of 6 times 6, which is going to be 18 meters. So in 6 seconds, with the velocity constantly increasing, the person covered 18 meters. Okay, now let's go back to our earlier one where we were going a steady 1 meter per second for 6 seconds. And look at this. Now at the end of that, if you remember, we went 6 meters. And in this case, we have the area is the base times the height, so it's 1 times 6. So 1 times 6 equals 6 meters. So that gives us the distance that we traveled. So with the velocity versus time graph, we can know the velocity. We can derive that. We can derive the distance. And we can derive the acceleration. We can derive everything that we need to know from a velocity versus time graph. Okay. All right, so let's see. Make sure I've covered everything before I go to an example problem here. Okay, let's go to an example problem. Nope, let's not go to an example problem. Let's work these things out together. Okay. Let's say I have let's see what I can do here. All right, let's work with here. All right, I have a velocity versus time graph. I'm going to give you a velocity versus time graph. And I'm going to have a constant velocity of 2 meters per second. How does that translate to a distance versus time graph? How would I draw that on there? Okay, so it's actually very simple. This is very constant, so every second I'm going to move 2 meters, right? It's 2 meters of velocity equals 2 meters per second. So every second I'm moving 2 meters. So my first second, 2 meters. My second one will be 2 more meters, so that'll be 4. My third one will be 6. And so I will have a slope that looks like this. Obviously, I didn't do that one very well. Okay, so I will have a slope that looks like that. All right, pretty straightforward. That just tells us what the slope of our line will be, and so we can just draw the thing. We can just do our our slope thing and figure out what that line's going to be. Very, very simple and straightforward. Okay, what if I have a velocity that is, let's say, kind of sloped like this. Okay, I'm trying to draw this so that it was a half a meter per second. So at 2 meters, I went 1 meter and so forth. But it's changing, right? I'm changing so that at the first second, I'm going to go how far? I'm going to go half a meter. But at the second, I'm going 1 meter per second. So I will then go 1 meter past that. So at 2 seconds, I'll be at 1.5. At 3 seconds, I'll be going 1.5. So I need to add. So I'll be going 3. 1.5 plus 3. At 4 seconds, I add another 1.5. Let's see, I'll be going 3. At 3 seconds, I'll be going 1.5 meters per second. So, is that right? Let's see. 0, 0.5, 1.5, 3. Yeah, at 4, I will be going 2. So I go up here. Now I'm going 5 meters per second. And so you can see that there is a curve going as I'm going faster and faster as I'm speeding up. So when I have a straight slope, non-zero slope on my velocity versus time graph, you can see that I have a curved slope on my distance versus time graph because my distance is increasing. The amount of distance I go each second is increasing because I'm going faster each second. So I cover more distance each second. Now, if I'm slowing down, if I've got a negative slope and I'm slowing down each second, I'm going to, let me change colors here so it's a little bit easier. Or let me just do this. Let's say I'm slowing down. And so each second I'm going to cover less distance because I'm slowing down until I stop, right? So I've gone some distance from my starting point. So I started, let's say, at the end of the block going 25 miles an hour, and I steadily slowed down to 0. And at 5 seconds, I reached 0, and I just stay there at the stop sign until I either back up or go forward or never leave the stop sign, just stay stopped. And that's what that would look like because I'm going less and less distance with each second because I'm going slower each second, covering less distance. Okay, so that's how you translate between these. Now, one thing I haven't gone into is I could be accelerating. Now, if I have a graph like this, and you see we go into negative velocity area, what happens is, and you can kind of picture this, this isn't actually realistic, but this is something that we can envision. I'm driving this way, but I'm slowing down as I'm driving this way, slowing down, and I reach 0. And then all of a sudden, this is actually accelerating in the opposite direction. I'm going faster and faster in the opposite direction. I'm covering more and more distance in the negative direction. All right, that makes sense, I hope. So I came down, I stopped, and instantly I reversed and went back the opposite direction. So what would this look like? I would be going back in the opposite direction. From where I started. In this case, I've gone a distance away from my destination because I was moving forward, and now I'm going backwards. And I'm going faster and faster and faster. And if I reach this spot and I stop, I will, and I mean instantaneously stop, I will just reach a point where I just stop, and now I'm like this. And this is possible. You've run your car into a wall because you haven't seen it because you're backing up and you just stop or, you know, something like that. But you can actually have this kind of situation. A lot of times you will go back in the other direction and you will slow down, cover less and less and less distance until you stop. Okay, so the slope, the direction that this goes has a lot to do with this. And you can actually go in the opposite. You can just keep going faster and faster in the negative direction, or slow down, get to where you're going and you stop, right? So be mindful. You will need to interpret graphs like this and understand how to do that. So make sure you understand what I just told you. All right, so let's work on this problem. A cheetah sees a gazelle it wants to catch. It begins running, and a mark is placed on the number line above to represent the distance the cheetah runs each second. Fill in the table below and create a distance versus time, dVt, and a velocity versus time, vVt graph. Show the slope of the vVt graph is the acceleration. Now, a lot of times in IB, they will ask you a question, especially on the free response test. Show the slope of something. Prove that this thing is true. Show how this works. And they want you to show that you understand the concept by manipulating the equations. And so I'll show you. This one is pretty straightforward and easy to do, and we'll work on that. Okay, so the first thing that we want to do, and all of a sudden my pen is not working. Here we go, got my pen working. All right, so the first thing that they want us to do is to fill in the table. So let's fill in the table with the results of this. So this cheetah starts running, and in the first measurement that we have at time 0, he's gone 0. He's up here, he has gone 0 meters, right? That's where he started out from what's called at rest, not moving. And so at time 0, he's moved 0 meters. All right, at time 1, he has moved, so this is time 0, 1 second, 2 seconds, 3, 4, and 5. At 1 second, he's moved 2 meters. At 3 seconds, he's gone 6. Is that right? Yeah. 1 second, 2 meters. 2 seconds, 6 meters. 3, he's gone 12. 4, he's gone 20. And 30, I'm sorry, at 5, he's gone 30. Okay, so let's fill in the rest of this table here. Delta T, again, delta is change in time. So the change in time from 0 to 1 second is 1 second. Change in time from 1 second to 2 seconds is 1. All of these, delta T is 1. The delta meters, the delta distance, change in the distance that he's run. All right, so on second 1, the change is 2 meters. He's gone from 0 to 2. 2 minus 0 is 2. 6 minus 2 is 4. 12 minus 6 is 6. 20 minus 12 is 8, and 30 minus 20 is 10. So 2, 4, 6, 8, 10. Now, the velocity, remember we stated this a little bit earlier, is distance over time. And remember, it's the slope of the graph. If we graph this over here, the VVT graph, we should get 2 meters per second, a slope, 2 meters per second. But we'll see if we get that or not. But distance over time, remember the delta change in distance over change in time, and that's what we have, delta time, delta distance. So 2 divided by 1 is 2, 4 divided by 1, 4, so you can see how this is going. All right, so here is the change in the cheetah's velocity over time. Let's go ahead and graph this. Okay, so let me get a good color here. All right, so we're going to graph the velocity versus time first, because I think that's going to really open up and let you see how the distance versus time works out. We're going to directly do distance versus time, but we're going to talk about it. So let me get the velocity versus time done first. All right, so at time 0, we have 0 velocity. At the first second, time 1, it is 2 meters per second. Time 2, it is 4 meters per second. Time 3 is 6. Get that in there. 4 is 8. Do the best I can with that. And 5 is 10. And so I didn't draw these dots in a very good place. I also didn't have the markings very even, but we basically have a slope line like that. Okay. This is showing that we have a very, we don't have a our velocity is changing. Lost the term in my mind. Our velocity is varied, but it's a constant rate. Our velocity, there we go. Our velocity is changing at a constant rate, and it gives us the straight line with a positive slope because we're speeding up. If we were slowing down, it would be a negative slope, right? Okay. So let's see how this works with the the distance versus time. So at the first second, we are at 2 meters, which is about right here. We had 0 at 0. At 2 seconds, we are at 6, which is about right here. At 3, we have 12, which is about right here. Is that right? Yeah. I think my 6 is in the wrong place. Let me fix that. Okay. 6 is right here. All right, 4, we are at 20. And 5, we are at 30. You can see this is not a straight line. This one is a bit curved. All right, you can see that there's a curve there because we're speeding up, each second we cover more distance. You can see the Y value is getting larger and larger. And so that tells us that our velocity is increasing, and therefore the distance we cover increases with each second. Okay, so there we have created distance versus time graph and the velocity versus time graphs. And so now we want to show that the slope of the velocity versus time graph is the acceleration. And because it has a slope, because it doesn't have a zero slope, it does have an acceleration. Remember, acceleration is the rate of change of velocity. And so we're changing the velocity here, and we're going to find out how much. How do we do that? We do it as a slope, as the acceleration. Acceleration is the slope. And again, I'm just going to do it is slope. And so I'm just going to do A for acceleration is rise over run. So it's 10 minus 0, 10 meters per second minus 0 meters per second over 5 seconds minus 0 seconds. And so it's 10 over 5 equals 2 meters per second squared. And so when you look at this, it makes sense. You can even see it up here. Every second we change, we increase our velocity and therefore the distance we cover by 2 meters per second. So in this second, the first second we go 2 meters per second. So we cover 2 meters. In the second, let's look at it down here on the graph. In the second one, we are going 2 meters per second faster. So 2 plus 2 is 4. And then 2 meters per second faster. 4 plus 2 is 6. 6 plus 2 is 8. 10 plus 2 is, 8 plus 2 is 10. And so each second increasing, I'll just do it this way, we're increasing velocity by 2 meters per second. And so each second, 2 meters per second per second. So that gives us the 2 meters per second squared. Okay, so we have just shown, that's exactly what they want us to show, is that the acceleration shows the rate of change, the acceleration of velocity. And we've done that because we've put it over time. Anything that goes, remember, over time is a rate of change. So there you go. There you have it. All you would have to do is put acceleration equals slope and then write out this portion here, and then that would be the answer that they're looking for. Okay, so next time we talk about acceleration, we will tie that all back into all of this, and we'll see more examples of things like this, of DVT and VVT, and next time we'll talk about acceleration and AVT, acceleration versus time graphs, and work everything back and forth between all these graphs. We'll see you then.